Hello, my name is Amy Knowlton, and on behalf of my co-authors, Dr. Tim Werner and Dr. Sam Weller, I will be providing a brief update about our recent weak rope research findings. Funding was provided by NOAA's Bycatch Reduction Engineering Program, and this information can be shared on social media. The potential benefits of using weaker ropes and fixed fishing gear to protect right whales were outlined in our 2016 paper. As a result of that study, 1,700-pound ropes and links have been mandatorily integrated to varying degrees into end lines in U.S. waters and are being trialed but are not yet mandatory in some Canadian waters. Why weak ropes? We need to remember that at present, the implementation of on-demand gear is focused just on seasonally closed areas, and as shown on these maps, these closed areas are limited spatially. As you have heard from others, serious and potentially lethal entanglements have not abated in recent years, despite closures being implemented more broadly. To further our understanding of how weak ropes may reduce entanglement severity, we have been working with Dr. Sam Weller, an associate consultant at TTI Marine Renewables Limited, who has used OrcaFlex software to simulate entanglements. We have also been using this software to simulate the hauling of gear to better understand where weak ropes could be effectively and safely used. To simulate entanglements, the OrcaFlex model was set up to accurately reflect the dimensions, weights, and configurations of lobster gear and various rope strengths, and at-sea load cell testing was conducted to inform the model. In addition, an anatomically accurate right whale model was integrated with basic behaviors such as swim speed and rolling. Here is one such simulation of an adult right whale becoming entangled in a 20-pot trawl in a water depth of 170 feet. For these simulations, we have evaluated the tension that is reached when this adult whale is swimming at varying speeds. For the behavior of the whale hitting the gear at various whale contact depths and rolling, the findings show that swim speed has the greatest effect on what maximum tension will be reached. In this graph, a whale swimming at 3 knots just barely exceeds the 1,700-pound tension at most whale contact depths, whereas a whale swimming at 7 knots definitely exceeds the 1,700-pound tension limit. If we look at the amount of time to reach a given tension threshold according to swim speed, rope strength, and whale contact depth, a whale swimming at 7 knots reached rope breakage of 1,700 pounds between 3 and 23 seconds. But for the 9,000-pound rope strength, the time to breakage was greater than 128 seconds, and in some cases longer than the simulation time of 160 seconds. We are also exploring the role of thrust. Working with Bill McClellan and Ann Pabst from UNCW and reviewing published literature to calculate these values for a 6-month-old, a 1-year-old, and a 30-year-old right whale. We can see that all of these thrust forces exceed the 1,700-pound tension. Time to reach the various rope strength thresholds was longer for the 30-year-old due to greater mass, but the difference between the 3 ages was less than around 10 seconds. However, the ability to reach these higher rope strength thresholds was not possible for the younger whales. This result is consistent with the result of our 2016 conservation biology paper, but we continue to examine this part of our study. And lastly, to further understand hauling situations, we integrated an 82-foot lobster boat hull into the model and assessed hauling tensions in relation to water depth, trawl length, and wave heights. We evaluated rope tension just before the first pot was brought on board to compare between the different scenarios. In waters less than 300 feet, the data indicated that if operational measures to reduce tension could be considered, it would be feasible to use weak rope or links throughout the entire end line. In waters greater than 300 feet, however, the 1,700-pound threshold was routinely exceeded, even if such operational changes were made. In closing, we have shown here that weak ropes can reduce the duration of an entanglement, which is an important metric to consider when trying to reduce this threat. Although prevention should be the ultimate goal, weak ropes implemented in the entire end line where feasible and used outside of closures are one important tool, amongst others, that can help achieve much needed risk reduction to ensure this species avoids extinction. Thank you very much for listening to our presentation.